Mars colonization is a death trap wrapped in adventure. Everyone thinks it is humanity's next home. They're wrong. Mars colonists aren't pioneers, they're guinea pigs in the most dangerous experiment humanity has ever attempted. Mars really doesn't want us there. And here is a question. If you were the first human to set foot on Mars, what's the very first thing you'd do? Let me know in the comments. I will pin the most creative answer. Now let's begin. Mars looks friendly from a distance. It has polar ice caps that advance and recede with the seasons. It has canyons that dwarf the Grand Canyon and volcanoes so massive they'd stretch from New York to Los Angeles if you placed them on Earth. Olympus Mons, the largest volcano in the solar system, towers about 22 kilometers above the surrounding plains. That's nearly 3 times the height of Mount Everest. The planet even has a day length remarkably similar to Earth's, 24 hours and 37 minutes. Surely a place with so many Earth-like qualities couldn't be that bad, right? Wrong. Devastatingly wrong. Because when you look closer, when you examine what the actual conditions are like on the surface, you realize that Mars is less like a harsh desert and more like a radiation-soaked freezer wrapped in a near vacuum with toxic soil. Let me paint you a more accurate picture. The Martian atmosphere is about 1% the density of Earth's atmosphere. That's not thin air like you'd experience on top of a mountain. That's essentially nothing. The atmospheric pressure on Mars is roughly equivalent to what you'd experience at an altitude of about 35 kilometers above Earth's surface, well into what we consider space. This has cascading consequences that affect everything from how water behaves to how radiation interacts with the surface. On Earth, our thick atmosphere acts like an invisible shield, protecting us from the worst of space radiation. Cosmic rays, high-energy particles that zip through the galaxy at nearly the speed of light, slam into our atmosphere and break apart long before they reach the ground. Solar flares and coronal mass ejections from our Sun get deflected by Earth's magnetic field and absorbed by our atmosphere. We're cocooned in layers of protection that we rarely think about. Mars has no such luck. The planet lost most of its magnetic field billions of years ago when its core cooled and stopped generating a dynamo effect. Without that magnetic shield, the solar wind, a stream of charged particles flowing from the Sun, has been slowly stripping away Mars' atmosphere for eons. What's left is that pitiful 1% we talked about earlier. And here's where the nightmare begins for any would-be colonist. Make sure to hit that subscribe button and give this video a thumbs up. Your support helps me continue researching and sharing the wonders and challenges of space. According to measurements taken by NASA's Curiosity rover, using its radiation assessment detector, an instrument specifically designed to measure the radiation environment on Mars, astronauts on the Martian surface would be exposed to about 230 millisieverts of radiation per year. Now let me put that number in perspective for you. The average person on Earth receives about 3 millisieverts per year from background radiation, cosmic rays that make it through our atmosphere, radon gas, medical procedures, and so on. 3 millisieverts. On Mars, you'd get 230. That's more than 75 times the radiation exposure you'd get on Earth. But it gets worse. During the journey to Mars, which takes anywhere from 6 to 9 months depending on the orbital positions of Earth and Mars, astronauts would be exposed to even higher levels of radiation because they'd be traveling through deep space without any planetary protection at all. Studies published in 2026 in the European Physical Journal Plus calculated that a round-trip Mars mission could expose astronauts to radiation doses that create a 5 to 10% increase in their lifetime risk of fatal cancer. The upper confidence interval of these estimates approaches 20% when you include cardiovascular disease and other radiation-induced health problems. 20%. Imagine signing up for a mission knowing that you have up to a 1 in 5 chance of dying from radiation exposure alone. And we're not just talking about cancer that might develop decades after you return, we're talking about acute risks during the mission itself. Damage to your central nervous system, cognitive impairment, cardiovascular problems, and a weakened immune system that makes you vulnerable to infections in an environment where medical care is extremely limited. But radiation is just the beginning of the story. It's the invisible monster that attacks your DNA cell by cell, day after day. There are other threats on Mars, visible, tangible, and equally deadly. The regolith, that fine reddish dust that covers the planet, isn't just dirt. It contains perchlorates, toxic compounds that interfere with thyroid function in humans. These chemicals are present at concentrations of about 0.5% to 1% by weight in Martian soil. If ingested or inhaled regularly, they could cause serious health problems. The dust itself is also a mechanical hazard. Under an electron microscope, Martian dust particles look like tiny shards of glass, sharp, angular, and extremely fine, much finer than desert sand on Earth. This dust will get everywhere. It will infiltrate seals, coat solar panels, scratch helmet visors, and irritate lungs if breathed in. The Apollo astronauts dealt with lunar dust, which shares similar properties, and they reported that it smelled like gunpowder, stuck to everything, and was impossible to clean off completely. Martian dust presents similar challenges, with the added bonus of being chemically toxic. Then there's the temperature. Mars is cold. Brutally, bone-chillingly cold. The average temperature on Mars is around -63 degrees Celsius. But that's just the average. At the poles during winter, temperatures can plunge to -125 degrees Celsius. Even at the equator during summer, the warmest place and time on Mars, temperatures might briefly reach a balmy 20 degrees Celsius during the day, only to plummet to -73 degrees Celsius at night. Why such extreme temperature swings? Again, it comes back to that wisp of an atmosphere. On Earth, our thick atmosphere acts like a blanket, retaining heat and moderating temperature changes between day and night. Mars doesn't have that luxury. Without a substantial atmosphere to hold on to heat, surface temperatures fluctuate wildly based on whether the sun is up or down. Living in such an environment means your habitat needs to be an engineering marvel, a perfect pressure vessel that maintains Earth-like conditions inside while everything outside is trying to kill you. It needs to hold in breathable air at the right pressure and temperature, filter out dust, block radiation, recycle water and oxygen, and do all of this reliably for years or decades without failure. Because here's the thing, on Mars, there's no calling for help. No rescue mission can reach you quickly. Earth and Mars align favorably for travel only once every 26 months. If something goes catastrophically wrong, you're on your own for at least 2 years. Now let's dig deeper into what I consider the single most terrifying aspect of Mars colonization: radiation damage to the human body. Because unlike the cold or the dust or the lack of air, things we can engineer solutions for, radiation presents a problem that we can't simply build our way out of, not yet anyway. When we talk about space radiation, we're really talking about two main culprits: galactic cosmic rays and solar particle events. Let's start with galactic cosmic rays, or GCRs. These are atomic nuclei that have been accelerated to nearly the speed of light by supernova explosions, colliding neutron stars, and other violent cosmic events happening across the galaxy. They've been traveling through space for millions or even billions of years, and they carry enormous amounts of energy. GCRs are made up mostly of protons, about 85%, with another 12% being alpha particles, and the remaining 3% consisting of heavier nuclei like carbon, oxygen, silicon, and iron. It's these heavy nuclei called HZE particles, high charge and energy, that scientists are particularly worried about. When an HCE particle passes through your body, it doesn't just damage one cell. It creates a track of destruction, ionizing atoms and breaking chemical bonds along its entire path. Picture a microscopic bullet tearing through tissue, leaving a trail of damaged DNA, broken proteins, and cellular chaos in its wake. Your DNA is constantly being damaged and repaired. That's normal. Background radiation on Earth, oxidative stress from metabolism, copying errors during cell division, all of these cause DNA damage that your cells usually repair successfully. But HCE particles cause a different kind of damage. They create clustered DNA lesions, multiple breaks in close proximity that are much harder for cellular repair mechanisms to fix correctly. When repair goes wrong, you get mutations. Accumulate enough mutations in the right genes, and you get cancer. Research published by NASA's Human Research Program in 2024 showed that the types of cancer most strongly associated with space radiation exposure include leukemia, lung cancer, stomach cancer, and colon cancer. But here's what's truly unsettling. We don't have good epidemiological data for the kind of radiation exposure astronauts would experience on a Mars mission because no human population on Earth has ever been exposed to anything quite like it. All of our radiation risk models are based primarily on studies of atomic bomb survivors from Hiroshima and Nagasaki, along with data from radiation therapy patients and nuclear workers. But those exposures involved gamma rays and neutrons, different types of radiation delivered in very different dose patterns. The quality factor, which is how much biological damage a given type of radiation causes, is much higher for HCE particles than for the gamma rays we have data on. We're extrapolating from imperfect data, which means our risk estimates could be significantly underestimating the true danger. A study published in PLOS One analyzed this uncertainty and concluded that for a Mars mission lasting around 1,000 days, roughly 250 days travel to Mars, 500 days on the surface, and 250 days return, the uncertainty in cancer risk estimates ranges over a factor of 4 or more. In other words, we genuinely don't know whether the increased lifetime cancer risk is 3% or 12%. That's not a comforting margin of error when you're gambling with human lives. But cancer isn't the only concern. Recent research has revealed that radiation exposure also significantly increases the risk of cardiovascular disease. A 2020 study published in the journal NPJ Microgravity identified radiation-induced cardiovascular damage as one of the red risks for Mars missions, the highest priority risks based on both likelihood and severity. The mechanisms aren't fully understood yet, but evidence suggests that radiation causes inflammation and damage to the endothelium, the inner lining of blood vessels. Over time, this leads to atherosclerosis, heart attacks, and strokes. Then there's the brain. And honestly, this might be the most disturbing part of the whole radiation story. Studies on mice exposed to radiation similar to what astronauts would experience have shown alarming cognitive effects. The radiation damages neurons and disrupts neural networks, leading to problems with memory, learning, decision-making, and mood regulation. Imagine being on Mars, millions of kilometers from home, dealing with life-threatening emergencies and finding that your ability to think clearly and make good decisions has been compromised by the very environment you're trying to survive in. A paper published in 2013 titled "How Safe is Safe Enough? Radiation Risk for a Human Mission to Mars" raised these concerns explicitly. The authors noted that damage to the central nervous system represents a qualitative difference in risk that goes beyond cancer and cardiovascular disease. These are effects that could impair mission performance in real time, not just create health problems years down the line. An astronaut experiencing cognitive decline during a critical repair operation could endanger the entire crew. Now you might be thinking, can't we just shield ourselves better? build thicker walls, use water or polyethylene as shielding, maybe bury habitats under Martian regolith. These are all strategies that have been proposed and studied extensively. The problem is that shielding in space is complicated. For solar particle events, sudden bursts of radiation from the sun during solar flares and coronal mass ejections, shielding works reasonably well. These events consist mostly of lower energy protons that can be stopped by a few centimeters of aluminum or several centimeters of water. You can design a storm shelter inside your spacecraft or habitat where astronauts can retreat during major solar events. Mars itself provides some shielding just by being there. Half the sky is always blocked by the planet itself, cutting exposure roughly in half compared to deep space. But for galactic cosmic rays, shielding is far less effective. GCRs are so energetic that stopping them requires massive amounts of material. And here's the cruel twist. When high-energy particles slam into shielding material, they create secondary radiation through nuclear interactions. Heavy shielding can actually make the radiation environment worse for certain particle energies. It's like trying to stop a bullet with a brick wall, only to have fragments of brick become additional projectiles. If you're finding this information valuable and want to learn more about the challenges of surviving on Mars, I highly recommend checking out my video called "Why Your First Year on Mars Would Be the Hardest." It goes into detail about the physical and psychological toll of adapting to Martian conditions. You can find it linked in the description below. The most effective shielding would be a strong magnetic field, like Earth's magnetosphere, that deflects charged particles before they ever reach you. Some scientists have proposed creating an artificial magnetic field around Mars, a massive engineering project that would require placing a powerful magnetic dipole at the Mars-Sun-Lagrange point, a gravitationally stable location between Mars and the Sun. Computer simulations suggest this could potentially increase atmospheric pressure over time by reducing atmospheric loss and might provide some radiation protection, but we're talking about a megastructure that would require technology and resources far beyond anything we can currently deploy. This is a solution for a mature interplanetary civilization, not for the first waves of colonists. Another approach that's been seriously studied is pharmaceutical countermeasures, drugs that could reduce radiation damage. Antioxidants can help neutralize free radicals created by radiation. Other compounds can stimulate DNA repair mechanisms or protect specific types of cells. NASA has tested various radioprotective agents, and some show promise in animal studies. But the effectiveness in humans for chronic, long-term exposure to mixed radiation fields remains uncertain. And of course, any drug powerful enough to significantly alter your cellular response to radiation is likely to have side effects, especially when taken continuously for years. There's also the intriguing but speculative idea of induced hibernation or torpor. If astronauts could be placed in a hibernation-like state during the journey to Mars, their metabolic rate would drop, potentially reducing the biological impact of radiation exposure. Research published in early 2026 explored this concept, noting that hibernating animals show increased resistance to radiation damage. The European Space Agency has funded preliminary studies on inducing torpor in humans for spaceflight. But this technology is still firmly in the realm of experimental research, not something we could deploy for a mission launching in the next decade. So where does this leave us? The radiation problem is real, it's serious, and we don't currently have a complete solution. Does this mean Mars colonization is impossible? Not necessarily. But it does mean we need to be honest about the risks. Early Mars colonists would essentially be accepting a significantly elevated health risk in exchange for being part of humanity's greatest adventure. Some people might find that trade-off acceptable. Explorers throughout history have faced mortal danger for the sake of discovery and expansion. But there's a difference between understanding and accepting risk versus being kept in the dark about it. And there's also the question of ethics. Is it acceptable to send people on a mission knowing they face a 10 or 20% increased risk of fatal disease? What about sending younger astronauts who would face decades of life after the mission, during which radiation-induced cancers could develop? These are questions that go beyond engineering and venture into philosophy, medical ethics, and societal values. The latest research from 2026, including comprehensive reviews in physics journals and aerospace medicine publications, makes clear that radiation risk mitigation remains one of the highest priorities for Mars mission planning. Scientists are exploring every possible avenue: better shielding designs, pharmaceutical interventions, personalized risk assessment based on individual genetics, advanced monitoring and early detection of radiation damage, and even selection of astronauts based on their natural resistance to radiation effects. But here's what keeps me up at night. Radiation is just one problem on a long list. It's the one that gets the most attention in scientific literature because it's quantifiable and we can study it. But Mars has so many other ways to kill you or make your life miserable that we need to talk about those too. Let's talk about what happens to your body in low gravity, because this is where things get really weird. Mars has about 38% of Earth's gravity. That might not sound too bad at first. After all, 38% is a lot more than the zero-gravity astronauts experience on the International Space Station, right? Surely that's enough to keep your body functioning normally. Wrong again. And the terrifying part is that we don't actually know exactly how bad 38% gravity will be for long-term human health, because no human has ever lived in that environment for an extended period. We have excellent data on zero gravity from decades of space station missions, and obviously we know what one Earth gravity does, but 0.38 G, that's uncharted territory. We're going to send people to live in that environment for years, possibly for the rest of their lives, without really knowing what it will do to them. Here's what we do know from space station research. Zero gravity is catastrophic for the human body over time. Astronauts on the ISS lose bone density at a rate of about 1 to 2% per month. That's 12 to 24% per year. Your bones literally dissolve because without gravity constantly loading your skeleton, your body decides it doesn't need to maintain all that expensive, metabolically costly bone tissue. The body is ruthlessly efficient. Use it or lose it. The bone loss isn't uniform either. It's concentrated in load-bearing bones, your hips, your spine, your legs. After 6 months in space, an astronaut's bone density can resemble that of an elderly person with advanced osteoporosis. The lost bone material gets dumped into the bloodstream, increasing the risk of kidney stones and potentially causing cardiovascular problems. And here's the kicker: when astronauts return to Earth, they can regain some of that lost bone mass through intensive exercise and proper nutrition, but they never fully recover. Some of that bone is gone forever. Now, astronauts on the ISS exercise for about 2 hours every day, using specialized equipment to combat bone loss and muscle atrophy. Even with that aggressive exercise regimen, they still experience significant degradation. On Mars, you'd have some gravity helping you out, but would it be enough? Mathematical models suggest that 38% gravity is probably not sufficient to maintain bone health without intensive intervention. You'd likely still need extensive daily exercise, possibly for even longer than 2 hours, just to slow the deterioration. Then there's muscle atrophy. In zero gravity, astronauts lose muscle mass and strength rapidly, especially in their legs and lower back. Muscles can atrophy by up to 20% during a 6-month mission despite rigorous exercise protocols. Again, Mars gravity might help, but probably not enough to prevent significant muscle loss over years or decades. Imagine being a Mars colonist and finding that after 5 years on the planet, you couldn't stand up in Earth gravity even if you wanted to. Your muscles and bones would have adapted so thoroughly to Mars that returning to Earth would be physiologically impossible. This raises a profound question. Would Mars colonists effectively be trapped there, not by choice or circumstance, but by biology? If spending a decade on Mars renders you physically incapable of surviving Earth gravity, then you haven't just moved to another planet, you've permanently severed your connection to the world where humans evolved. You and your children would become a new branch of humanity, adapted to a different world, unable to ever return home. But wait, there's more. And it gets weirder. One of the most unexpected discoveries from long-duration spaceflight is something called Spaceflight-Associated Neuroocular Syndrome, or SANS. This condition affects roughly 70% of astronauts on long missions and causes structural changes to the eye and optic nerve that can permanently impair vision. Here's what happens. In zero gravity, fluids in your body redistribute. On Earth, gravity pulls blood and other fluids down toward your legs. Your cardiovascular system is designed to pump blood upward against gravity to supply your brain. But in zero gravity, that system keeps pumping blood toward your head with the same force, even though there's no gravity to fight against. The result is that fluid accumulates in your upper body and head, creating a chronic state of elevated intracranial pressure. This fluid pressure causes the back of the eyeball to flatten, the optic nerve to swell, and in some cases small folds or kinks to develop in the choroid layer of the eye. Astronauts experience vision changes, difficulty focusing on nearby objects, hyperopic shifts that require them to use reading glasses in space, even if they had perfect vision on Earth. NASA considers SANS one of the highest risk factors for long-duration missions because we don't fully understand the mechanisms, we can't reliably predict who will be affected, and we don't have effective countermeasures yet. Will Mars gravity be enough to prevent SANS? We simply don't know. Fluid redistribution might still occur, just to a lesser degree. Or maybe 38% gravity hits some unfortunate middle ground where it's enough to cause problems but not enough to prevent them. We won't know until we have people living on Mars for months or years, serving as unwitting experimental subjects in the largest human physiology study ever conducted. The cardiovascular system faces other challenges too. In zero gravity, the heart doesn't have to work as hard to pump blood because there's no gravitational resistance. The heart is a muscle, and like any muscle, it atrophies when not used at full capacity. Astronauts return from space with slightly weakened hearts. Studies using advanced imaging techniques have shown that the heart becomes more spherical in zero gravity, changing from its normal elongated shape. These changes reverse after returning to Earth, but they raise questions about long-term cardiovascular health in reduced gravity environments. There's also growing evidence that space radiation and reduced gravity have synergistic effects. They're worse together than the sum of their individual impacts. Research published in 2026 specifically highlighted this interaction. Radiation damages cells, including the cells that line blood vessels. Reduced gravity alters blood flow patterns and pressure. Together, these factors might accelerate cardiovascular disease in ways that neither factor alone would predict. Your immune system takes a hit too. Multiple studies have documented immune system dysfunction in astronauts during and after spaceflight. T-cell function decreases, making you more susceptible to infections. Latent viruses that your immune system normally keeps in check, like herpes simplex and varicella zoster, can reactivate. Imagine being on Mars, cut off from advanced medical care, dealing with a compromised immune system in an environment where even a minor infection could become life-threatening because you can't evacuate to a hospital. Wound healing is also impaired in reduced gravity. Research on the ISS has shown that cuts and injuries heal more slowly in space. This has obvious implications for Mars colonization. Any injury, from a simple cut to a broken bone, becomes more serious when your body's ability to repair itself is compromised. And since Mars is an inherently dangerous environment, sharp rocks, equipment malfunctions, extreme temperatures, injuries are going to happen. Now let's talk about something that doesn't get discussed enough in popular media: pregnancy and child development on Mars. If we're talking about genuine colonization, not just a temporary outpost but a permanent human presence, then eventually people are going to want to have children. But what happens when a human fetus develops in 38% gravity? We have essentially zero data on this. It's never been studied in humans because we've never had pregnant women in space for obvious ethical reasons. Animal studies on the ISS and in simulated reduced gravity environments have shown concerning results. Pregnant rats exposed to simulated spaceflight conditions had offspring with developmental abnormalities, particularly in the vestibular system that controls balance. Mouse embryos develop differently in space, with some exhibiting skeletal and muscular defects. The human fetus develops in a very specific gravitational environment. Cell migration, tissue differentiation, fluid dynamics within the womb, the formation of the skeletal system, all of these processes evolved under Earth gravity. What happens when you change that fundamental parameter? We don't know. Maybe humans can develop normally in Martian gravity. Maybe the 38% is enough. Or maybe children born on Mars would face developmental challenges that we can't even predict. And if they do develop successfully, they would be adapted to Martian gravity from birth. Their bones and muscles would grow to match that environment. Which brings us back to that haunting question: could a child born on Mars ever visit Earth? Would their body, having never experienced 1G during critical developmental periods, be strong enough to handle Earth gravity? Or would Mars-born children be permanent residents of the red planet, biologically cut off from the ancestral home they've only seen in photographs and videos? There's something deeply unsettling about this prospect. We like to think of space colonization as expanding human civilization, giving us a backup in case something catastrophic happens to Earth. But if colonists and their descendants become physiologically incompatible with Earth, are they really expanding humanity, or are they becoming something else? A new species, perhaps, separated not by millions of years of evolution, but by a single generation born under alien skies. The psychological implications are staggering too. Imagine being a teenager born on Mars, knowing that your parents came from Earth, seeing videos of blue skies and oceans and forests, but understanding that you can never go there. Your body wouldn't survive. Earth is permanently off limits to you. That's a unique form of exile, and we have no idea how it would affect the human psyche across generations. These aren't hypothetical thought experiments designed to sound dramatic. These are real questions that colonization would force us to confront. The scientific literature is full of papers with titles like Reproductive Health Risks for a Journey to the Red Planet and Developmental Biology in Reduced Gravity Environments. Researchers are genuinely worried about these issues because they represent fundamental unknowns about human biology in a new environment. Now let's shift gears and talk about something that sounds mundane, but could be absolutely critical: food. You need to eat on Mars, that sounds obvious, but the challenges of maintaining adequate nutrition on another planet are far more complex and serious than most people realize. On Earth, if your crops fail, you can import food from somewhere else. On Mars, if your crops fail, you starve. There's no backup. Resupply missions from Earth would arrive every 26 months at best, and they could only carry limited cargo. A Mars colony would need to become agriculturally self-sufficient relatively quickly, or it would be living on the edge of famine constantly. NASA has identified inadequate food and nutrition as one of the red risks for Mars missions, right up there with radiation and behavioral health. And for good reason. Growing food on Mars presents challenges that make terrestrial agriculture look simple by comparison. First, there's the regolith problem we touched on earlier. Martian soil isn't really soil in the biological sense. It's regolith, loose, rocky material that's never been touched by life. Real soil on Earth is a living ecosystem teeming with microorganisms, fungi, decomposed organic matter, and nutrients in forms that plants can access. Martian regolith has none of that. It's sterile, chemically reactive, and contaminated with those toxic perchlorates we mentioned. A fascinating study published in May 2026 explored using beneficial fungi to potentially convert Martian regolith into something more like actual soil. These fungi species can drive nutrient cycling and help plants absorb nutrients even under stress conditions. Researchers are investigating whether these fungal partnerships could help establish agriculture on Mars. It's promising work, but it's still very much in the experimental stage. The first colonists won't have proven biological systems to rely on. They'll be testing these ideas in real time, with their lives depending on the results. Even if you could somehow amend the regolith to make it suitable for plants, you'd need to grow crops in pressurized greenhouses because the Martian atmosphere is unbreathable and the pressure is too low for liquid water to exist on the surface. These greenhouses would need to maintain Earth-like atmospheric pressure, provide appropriate lighting since Mars receives only about 43% as much sunlight as Earth, maintain proper temperature and humidity, and protect plants from radiation. That last point is crucial. Plants are affected by radiation too. High-energy particles damage plant DNA just like they damage human DNA. Studies on the ISS have shown that plants grown in space exhibit stress responses, altered gene expression, and reduced growth rates. The radiation environment on Mars would likely affect crop yields, plant health, and the nutritional content of the food produced. You might successfully grow potatoes on Mars, but they might be nutritionally inferior to Earth potatoes, containing lower levels of vitamins and minerals due to radiation-induced stress. Then there's the water problem. Plants need water and lots of it. While Mars has water ice at the poles and subsurface ice at various locations, extracting and purifying that water requires significant energy. Every drop of water would need to be carefully recycled. A closed-loop life support system would recover water from plant transpiration, human waste, humidity in the air, everything. NASA has been developing these systems for decades, and they've gotten quite good at water recycling on the ISS, achieving about 93 to 94% recovery rates. But that remaining 6 to 7% loss adds up over time, meaning you'd need to continually extract new water from Martian ice to make up the deficit. Let's talk about the psychological and physiological impacts of food monotony. Space station astronauts frequently complain about food fatigue, getting tired of eating the same limited menu repeatedly. On a Mars colony, especially in the early years, dietary variety would be extremely limited. You'd be eating whatever crops could be reliably grown in Martian greenhouses supplemented by stored provisions from Earth. Research shows that dietary monotony isn't just unpleasant, it has real health consequences. People eating repetitive diets tend to consume fewer calories, even when food is available, because they lose appetite. They also tend to develop micronutrient deficiencies because they're not getting the variety needed for complete nutrition. On Mars, where you're already dealing with radiation exposure, bone loss, muscle atrophy, and a host of other stressors, inadequate nutrition could be the factor that pushes someone over the edge into serious health problems. NASA has conducted food acceptability testing under Mars-like conditions, high caloric demands, compressed meal times, no food warmer, no fresh food. The results show that maintaining adequate nutrition under these constraints is genuinely difficult. People get tired of eating even when they know they need to. Food becomes utilitarian rather than pleasurable, which sounds like a minor quality of life issue, but can actually impact mental health significantly. And speaking of mental health, we need to address what is perhaps the most underestimated danger of Mars colonization, the psychological toll. Imagine being confined to a small habitat with the same handful of people for years, breathing recycled air, drinking recycled water, eating monotonous food, never feeling real sunlight on your skin, never breathing fresh air, never seeing a tree or an animal or any living thing except your crewmates and whatever crops you're growing. The isolation would be absolute. Even communication with Earth would be delayed by between 3 and 22 minutes one way, depending on where the planets are in their orbits. You couldn't have a real conversation with anyone back home. No video calls where you can see your family's reactions in real time. Every interaction would be asynchronous. Send a message, wait 20 minutes or more, receive a response, wait again. This fundamental disconnect from everyone you've ever known except your small crew would be psychologically devastating for many people. Antarctica research stations provide our best analog for this kind of isolation. Scientists who winter over at places like the South Pole Concordia Station experience a phenomenon called winter over syndrome, a combination of depression, cognitive impairment, insomnia, and irritability that develops during the months of isolation and darkness. And they're on Earth, in an environment that's harsh but not immediately lethal, knowing that rescue is possible if something goes catastrophically wrong. Mars colonists would face isolation that makes Antarctica look like downtown Manhattan. They'd be dealing with genuine life or death stakes every single day. One equipment failure, one habitat breach, one mistake in protocol could kill everyone. The psychological pressure of living in an environment that's actively trying to kill you, combined with isolation, confinement, and monotony, would be crushing. Studies on long-duration spaceflight have documented interpersonal conflicts, depression, anxiety, and something called salutogenic effects, where the awe and privilege of being in space provides psychological benefits that partially offset the stresses. Astronauts often report that seeing Earth from space, experiencing the overview effect, and feeling like they're part of something historically significant helps them cope with the challenges. But would Mars colonists experience those same benefits? After a few months or years, would the novelty wear off? Would looking out at the same desolate red landscape day after day lose its inspirational quality and become just another reminder of how far from home you are? The psychological research suggests that yes, novelty effects wear off, and then you're left dealing with the baseline reality of your situation. There's also the question of behavioral health in mixed-gender, small group, high-stress environments. Research going back to submarine crews and Antarctic stations has shown that group dynamics can become toxic under these conditions. Personality conflicts get magnified. Small annoyances become major grievances. Social hierarchies and power dynamics can create resentment and dysfunction. NASA and other space agencies screen astronauts extensively for psychological stability, team compatibility, and stress resilience. They provide psychological support during missions and train crews in conflict resolution. But even with the best selection and training, problems arise. There have been documented cases of cosmonauts and astronauts experiencing psychological crises during long missions. On the ISS, there's at least the psychological safety valve of knowing you can return to Earth in a matter of hours if absolutely necessary. On Mars, there's no quick escape. You're committed for years. Imagine having a severe psychological breakdown on Mars. Severe depression, psychosis, extreme anxiety. These conditions require intensive psychiatric care and often medication. The medical facilities on an early Mars colony would be rudimentary. Psychiatric medications have shelf lives and can degrade, especially under radiation exposure. What do you do with a crew member who becomes suicidal or violent? There are no easy answers to these questions, and they're questions that would inevitably come up during a long-term colonization effort. Then there's the issue of purpose and meaning. Astronauts on the ISS are there for a few months, conducting specific research, and then they go home. They have a clear mission with defined objectives and an end point. Mars colonists would be settling in for the long haul. What happens when the initial excitement wears off and you're just living a difficult, dangerous life with limited comforts and few rewards? How do you maintain morale and a sense of purpose when every day is a struggle for survival? Some researchers have proposed that Mars colonies would need robust social structures, cultural practices, and opportunities for personal growth and achievement to maintain psychological health. You'd need not just survival, but reasons to thrive. Art, music, science, exploration, community building. These would be essential, not luxuries. A Mars colony that focused purely on survival and efficiency would likely be a psychologically unhealthy place to live. There's something deeply human about this challenge. We're not just machines that need food, water, and oxygen. We're social creatures who need connection, novelty, beauty, and meaning. Taking humans away from the rich sensory environment of Earth, the colors, sounds, smells, textures that our brains evolved to process, and putting them in a sterile, monotonous habitat on Mars is an experiment in sensory deprivation and psychological endurance. Let's talk about something that sounds technical, but could make or break a Mars colony: infrastructure and resource utilization. Because here's the reality: you can't ship everything you need from Earth. It's physically impossible and economically absurd. A successful Mars colony would need to manufacture, repair, and create things using local resources. This concept is called in situ resource utilization, or ISRU, and it's both our greatest hope and a massive challenge. Think about everything you use in a single day. Your clothes, your electronics, the building materials in your home, the tools you work with, the medical supplies you might need. Now imagine that all of that has to either be brought from Earth at a cost of tens of thousands of dollars per kilogram, or made on Mars from local materials using technology that barely exists yet. The most critical ISRU application is producing oxygen and water. Mars' atmosphere is 95% carbon dioxide. Through a process called the Sabatier reaction, you can combine carbon dioxide with hydrogen to produce methane and water. Then you can electrolyze that water to get hydrogen, which you recycle back into the reaction, and oxygen, which you breathe. NASA's MOXIE experiment on the Perseverance rover successfully demonstrated oxygen production from Martian atmosphere in 2021. It worked. But MOXIE is a small-scale technology demonstrator. Scaling it up to life support levels for even a small crew requires much larger, more complex systems that need to run reliably for years. Water can theoretically be extracted from Martian ice deposits. Ground-penetrating radar from orbiters has identified subsurface ice at various locations, particularly at mid to high latitudes. But extracting that ice means you need power-hungry equipment to excavate and heat the frozen regolith, capture the released water vapor, and purify it. All of this requires energy, which brings us to another critical problem: power generation. Solar panels work on Mars, but they're less efficient than on Earth because Mars receives less sunlight, and frequent dust storms can coat panels, reducing output even further. The global dust storm of 2018 covered the entire planet and killed the Opportunity rover by blocking sunlight to its solar panels for months. Imagine being a Mars colonist when a global dust storm hits and your solar power output drops by 80%. You're suddenly running on emergency backup power, rationing electricity, turning off non-essential systems, and hoping your life support holds out until the storm clears, which could take weeks or months. Nuclear power seems like the obvious solution. Small modular reactors could provide reliable baseload power regardless of weather conditions. NASA has developed the Kilo Power reactor, designed specifically for space applications, which could generate 10 kilowatts of electrical power continuously for 10 years or more. That's enough for a small outpost, but larger colonies would need multiple reactors or much bigger systems, and you're now dealing with the challenges of nuclear fuel, radiation shielding, waste, heat management, and reactor maintenance. All of this on another planet with no existing infrastructure. Let's talk about manufacturing. Early Mars colonists would have limited manufacturing capability, basically whatever they brought with them. 3D printing has been proposed as a key technology for Mars, and it makes sense. You can theoretically print tools, spare parts, even structural components using Martian regolith as feedstock. Research published in 2026 discussed using additive manufacturing to build habitats and equipment on Mars from metallic materials. But here's the problem. Mars doesn't appear to have concentrated metal deposits like we have on Earth. Earth's geology, driven by plate tectonics, volcanism, and water-mediated chemical processes over billions of years, has concentrated metals into rich ore bodies that we can mine. Mars doesn't have plate tectonics, it's a geologically dead world. The metals are there, iron is literally rusting on the surface, but they're dispersed rather than concentrated. A study published in May 2026 examined whether Mars colonies might need to mine asteroids to get sufficient quantities of metallic materials. Some asteroids, particularly M-type asteroids, are essentially solid chunks of metal, iron, nickel, platinum group metals, just floating in space. The researchers calculated trajectories and energy requirements for mining missions that would retrieve metal from near-Mars asteroids and deliver it to the Martian surface. It's theoretically possible, but it requires spacecraft, propulsion systems, mining equipment, and a level of space infrastructure that wouldn't exist during the first decades of colonization. So the first Mars colonists would be operating with severe material constraints. Every tool, every piece of equipment, every spare part would be precious because replacing them would be difficult or impossible. This is fundamentally different from how we live on Earth, where if something breaks, you just buy a new one. On Mars, if your only wrench breaks and you can't manufacture a replacement, you might not be able to maintain critical life support equipment. That's not an exaggeration, it's a genuine survival risk. Medical care presents similar challenges. An early Mars colony wouldn't have a full hospital with surgical suites, imaging equipment, and comprehensive pharmaceutical supplies. You'd have what amounts to a well-equipped first aid station, maybe some limited surgical capability, and a stock of medications that's slowly degrading under radiation exposure. Research from 2026 specifically addressed how radiation degrades pharmaceuticals, reducing their effectiveness over time. Many medications need to be stored in cool, dark, stable conditions, exactly what you don't have on a spacecraft during a months-long journey or in a Mars habitat with temperature fluctuations and persistent radiation. What happens when someone needs an appendectomy? When someone breaks a bone in a way that requires pins and plates? When someone develops a serious infection that needs antibiotics you don't have or that have degraded? When someone has a dental emergency, a tooth infection, a broken tooth, and you don't have proper dental equipment? These aren't edge cases. These are common medical situations that occur in any population, and on Mars, they could be fatal. The concept of acceptable risk takes on new meaning in this context. On Earth, we've pushed medical mortality rates down to extremely low levels in developed countries. We expect that if we have a medical emergency, we'll receive professional care and probably survive. That expectation wouldn't hold on Mars. The medical care would be more comparable to what you'd find on an 18th century sailing ship, a trained person doing their best with limited supplies, high improvisation, and outcomes that are often uncertain. Psychologically, living with that level of vulnerability would be challenging. Every time you do something with even minor injury risk, climbing a ladder, operating machinery, going outside for EVA, you'd be acutely aware that a mistake could lead to medical complications that can't be properly treated. This constant low-level anxiety would be yet another stressor, adding to the psychological burden we discussed earlier. Communication infrastructure is another critical consideration. Early Mars missions would rely on direct Earth-Mars communication, but that only works when Earth is visible from Mars. Mars rotates every 24.6 hours, so Earth rises and sets in the Martian sky just like the Sun does. To maintain continuous communication, you'd need a network of relay satellites around Mars, plus additional relay satellites positioned throughout the inner solar system to handle periods when the Sun is between Earth and Mars, superior conjunction, which happens about once every 26 months and blocks direct communication for weeks. Building out that communication infrastructure requires launching multiple satellites, establishing ground stations on Mars, and maintaining all of that equipment. Early colonists would experience communication blackouts, periods where they truly are cut off from Earth with no way to send or receive messages. Imagine dealing with an emergency, a medical crisis, an equipment failure, a difficult decision, and not being able to even ask for advice from mission control. You're on your own, making life or death decisions with no support. Transportation on Mars is also more complicated than it sounds. The rovers we've sent to Mars travel slowly. Curiosity's top speed is about 4.2 centimeters per second, roughly 0.15 kilometers per hour. That's fine for a robotic mission that has years to explore a small area. It's useless for a human colony that needs to transport materials, explore for resources, and respond to emergencies. A colony would need faster rovers, probably pressurized vehicles that crews could drive for hours without wearing spacesuits. But building reliable vehicles on Mars is challenging. The dust gets into everything, wearing down seals and mechanical components. The extreme temperature cycles cause materials to expand and contract, leading to fatigue and failure. Batteries lose capacity in the cold. Lubricants behave differently in low pressure and low temperature. Every vehicle system needs to be designed and tested for Martian conditions, and even then, maintenance would be constant and critical. There's also the question of landing sites and expansion. The first Mars colony would probably be located near a confirmed subsurface ice deposit at a relatively low elevation, where the atmosphere is slightly thicker, and at a latitude where temperature extremes aren't quite as severe. But as the colony grows, you might need to establish outposts in other locations to access different resources or scientific sites. Each new outpost requires duplicating life support systems, power generation, and habitats. It's like building a new frontier town from scratch, except the frontier is actively lethal. Some futurists envision eventually terraforming Mars, altering the planet's environment to be more Earth-like. Release greenhouse gases to warm the planet, thicken the atmosphere, melt the ice caps, and maybe eventually create conditions where you could walk outside without a spacesuit. It's a beautiful vision, but the timescales involved are centuries or millennia, and the technological and ethical challenges are immense. The first Mars colonists wouldn't be living on a terraformed world. They'd be living in small bubbles of survivable environments surrounded by endless hostility. There's something both inspiring and terrifying about this level of challenge. Humanity has never attempted anything quite like this. Antarctic research stations and submarines are our closest analogues, but even those exist within Earth's protective embrace. Mars colonization would push human ingenuity, resilience, and adaptability to absolute limits. Now let's discuss something that rarely gets the attention it deserves, the economics of Mars colonization, because ultimately someone has to pay for all of this, and the financial realities are sobering. We're talking about the most expensive endeavor humanity has ever attempted, and the return on investment is unclear at best. NASA's estimates for a human Mars mission vary widely depending on the architecture, But most credible analyses put the cost somewhere between $100 billion and $500 billion just for the first mission. That's just to get people there and back safely. Establishing a permanent, self-sustaining colony would cost vastly more, potentially trillions of dollars over several decades. To put that in perspective, the entire Apollo program cost about $280 billion in today's money, and that was just to land 12 people on the Moon for brief visits. Mars is exponentially more difficult. The distances are greater, the mission durations are longer, the life support requirements are more demanding, and the stakes are higher. Who's going to pay for this? Government space agencies have limited budgets. NASA's annual budget is around $25 billion, a fraction of 1% of the United States federal budget. Even if NASA devoted its entire budget exclusively to Mars colonization, which would mean canceling everything else including the International Space Station, the James Webb Space Telescope follow-ups, and all planetary science missions, it would still take decades to accumulate the necessary funding. This is why private companies like SpaceX have entered the conversation. Elon Musk has stated that his ultimate goal is to establish a self-sustaining city on Mars with 1 million people. SpaceX is developing the Starship system specifically for this purpose, a fully reusable launch system designed to dramatically reduce the cost of reaching orbit and beyond. If successful, Starship could potentially reduce launch costs to a few $100s per kilogram rather than several thousand. But even with dramatically reduced launch costs, the economics remain challenging. Let's do some rough calculations. Suppose SpaceX achieves its goal of reducing launch costs to $200 per kilogram. A single person with life support equipment, habitat modules, supplies, and everything else they'd need for a Mars mission might mass 10,000 kilograms or more when you account for everything. That's $2 million just in launch costs per person. Multiply that by the hundreds or thousands of people you'd need for a viable colony, and you're still talking about billions of dollars in launch costs alone before accounting for developing the spacecraft, the habitats, the rovers, the power systems, and everything else. Where does the money come from? One model is that Mars colonization becomes a publicly funded scientific endeavor, justified on the grounds of expanding human knowledge and ensuring species survival. This is the Apollo model, government funding driven by geopolitical competition, national pride, and scientific curiosity. It worked for Apollo, but Apollo had clear Cold War motivations and a specific finish line: beat the Soviets to the Moon. Mars colonization doesn't have that same political urgency or clear endpoint. Another model is that private companies fund colonization with the expectation of eventual profit. But what's the profit model for Mars? What resources or services could a Mars colony provide that would generate revenue sufficient to justify the enormous investment? Some people point to asteroid mining. The asteroids contain vast quantities of valuable metals, platinum, gold, rare earth elements. But those resources are only valuable if you can bring them back to Earth, and the energy cost of doing so is enormous. It's almost certainly more economical to mine those same elements on Earth, even if they're less concentrated. The only scenario where asteroid mining makes economic sense is if you're using those materials in space rather than returning them to Earth, building space infrastructure, supporting Mars colonies, constructing spacecraft. But that requires an already existing space economy of sufficient scale to create demand, which doesn't exist yet. Tourism is sometimes mentioned as a potential revenue source. Wealthy individuals might pay enormous sums for the experience of visiting Mars, but the journey is long, dangerous, and uncomfortable. You're looking at 6 to 9 months in zero gravity on the way there, then time on Mars living in cramped habitats, then another 6 to 9 months to return. The total mission duration would be at least 2 years, possibly 3, depending on planetary alignments. And unlike space tourism to orbit, where you can return to Earth in a few hours if something goes wrong, a Mars tourism mission is committed. Once you launch, you're going all the way. The liability alone would be staggering. Scientific research could justify some level of funding. Mars is genuinely interesting scientifically. It might harbor evidence of past life. It offers insights into planetary formation and evolution, and it serves as a natural laboratory for studying geology and atmospheric science. But scientific research doesn't generate profit in the traditional sense. It generates knowledge which has value, but not the kind of value that attracts private investment seeking financial returns. Some advocates argue that Mars colonization should be viewed as insurance for humanity, a backup in case Earth becomes uninhabitable due to nuclear war, climate catastrophe, asteroid impact, or some other existential threat. From this perspective, the cost of Mars colonization is justified by the existential risk reduction it provides. Even if there's only a small probability of Earth-destroying catastrophe, the expected value of having a self-sustaining colony on another planet could be enormous. But this argument has problems too. First, even a worst-case scenario on Earth, full-scale nuclear war, runaway climate change, massive asteroid impact, would likely leave Earth more habitable than Mars currently is. Earth would still have breathable air, liquid water, a magnetic field, and a biosphere. Mars has none of those things. If your goal is species survival, it might make more sense to invest in preventing catastrophes on Earth or building survival infrastructure on Earth rather than trying to colonize a planet that's fundamentally hostile to human life. Second, a Mars colony wouldn't actually provide meaningful existential risk reduction unless it's genuinely self-sustaining, which means it needs to be able to survive indefinitely without any support from Earth. That's an incredibly high bar. It means manufacturing everything locally, including sophisticated electronics, medical supplies, and replacement parts for complex machinery. It means maintaining genetic diversity to avoid inbreeding. It means establishing a complete industrial base from scratch on another planet. We're probably talking about a population of at least tens of thousands of people with a highly developed infrastructure before you could truly say the colony could survive Earth's destruction. Getting from the first small outpost to a truly self-sustaining city would be the work of generations and would require sustained investment on a scale that's hard to even imagine. We're talking about an economic commitment that would dwarf the Manhattan Project, the Apollo program, and the interstate highway system combined, sustained not for a decade, but for a century or more. There's also the question of what happens if the funding runs out partway through. Suppose we establish a Mars colony with 100 people, and then political priorities shift, economic conditions change, or public interest wanes. Does Earth just stop sending supply missions? Do we abandon those people? The ethics of starting a colonization project without certainty that you can sustain it are troubling. You're potentially condemning people to death or creating a permanent underclass of colonists who are dependent on Earth's continued support, but have no guarantee of receiving it. Historical parallels are instructive here. European colonization of the Americas was funded by a combination of government sponsorship and private investment, with the expectation that colonies would eventually become economically productive through resource extraction, agriculture, and trade. And they did, though often at horrific human cost. But the Americas had breathable air, drinkable water, edible plants and animals, and indigenous peoples who were exploited but whose knowledge was crucial to colonial survival. Mars has none of those advantages. Every breath of air, every drop of water, every calorie of food has to be produced through technological systems that require constant maintenance and energy input. There's no indigenous population to exploit, thank goodness, from an ethical standpoint, but from a purely practical survival perspective, there's also no one to teach you how to live off the land, because there is no living off the land on Mars. Some economists have modeled Mars colonization scenarios and concluded that without a major technological breakthrough, fusion power, advanced AI, molecular nanotechnology, something that dramatically changes the cost structure. Mars colonies would remain economically dependent on Earth indefinitely. They'd be permanent welfare colonies, consuming resources without producing sufficient value to justify their existence from a purely economic standpoint. Does that mean Mars colonization is impossible? Not necessarily. It means that the motivation has to be something other than profit. It has to be ideological, aspirational, scientific, or philosophical. We'd be doing it because we want to, because we believe it's important for humanity's future, because we find it inspiring and meaningful, not because it makes economic sense. And honestly, there's something beautiful about that. Not everything humans do has to be justified by a profit margin. We fund art, music, fundamental scientific research, exploration, and countless other endeavors that don't generate economic returns, but that enrich our lives and expand our understanding. Maybe Mars colonization falls into that category, a grand project undertaken not for profit, but for the sheer ambition of it, for the knowledge gained, for the inspiration it provides, and for the long-term dream of becoming a multiplanetary species. But we need to be honest about what that means. It means accepting that Mars colonization will be extraordinarily expensive and economically unproductive for the foreseeable future. It means sustained public support and funding across decades and potentially centuries. It means accepting significant risks, including the possibility of failure and loss of life. And it means acknowledging that the people who go to Mars, especially in those first generations, will be undertaking a mission of immense hardship with limited material rewards. Let's shift our focus to the legal and ethical dimensions of Mars colonization, because this is where things get philosophically complex. Who owns Mars? Who has the right to colonize it? What laws apply there? And what are our ethical obligations when venturing onto another world? Currently, Mars is governed, to the extent that it's governed at all, by the Outer Space Treaty of 1967. This treaty, signed by over 100 countries, including all major spacefaring nations, establishes several key principles. First, outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. In other words, no country can claim to own Mars. Second, the treaty stipulates that space exploration shall be carried out for the benefit of all countries and shall be the province of all mankind. Activities must be conducted in accordance with international law, and countries bear international responsibility for national space activities, whether carried out by governmental or non-governmental entities. Third, the treaty prohibits placing weapons of mass destruction in orbit or on celestial bodies and restricts military activities on celestial bodies to peaceful purposes. Sounds reasonable, right? The problem is that the Outer Space Treaty was written in 1967 when Mars colonization was pure science fiction. The treaty's framers were primarily concerned with preventing the Cold War from extending into space and ensuring that no superpower could claim the Moon or other celestial bodies as territory. They weren't thinking about practical questions like, can a private company extract resources from Mars? Can a colony claim land for habitats and agriculture? Who has authority over criminal matters if someone commits a crime on Mars? The treaty says celestial bodies can't be appropriated by nations, but it doesn't explicitly address whether private entities can claim resources. This ambiguity has led to national legislation attempting to fill the gap. The United States passed the Commercial Space Launch Competitiveness Act in 2015, which grants U.S. citizens the right to own and sell resources they extract from asteroids and other celestial bodies. Luxembourg passed similar legislation. These laws essentially say, we're not claiming sovereignty over space, but our citizens can own what they mine there. Is this legal under the Outer Space Treaty? That's debatable. Some legal scholars argue it's compatible. You're not claiming the celestial body itself, just the resources extracted from it, similar to how fishing in international waters doesn't mean you own the ocean. Others argue it violates the spirit of the treaty by allowing de facto appropriation through resource extraction and establishing a first-come, first-served system that benefits wealthy nations and companies. Now imagine a Mars colony operated by a private company, say SpaceX. The company invests hundreds of billions of dollars to establish a settlement. Does that company have any special rights over the land it's using? Can it exclude others? Can it charge rent or fees? Under current international law, the answer is murky at best. The company can't claim sovereignty, but it arguably has a right to use the land for peaceful purposes. Whether that use right includes the ability to exclude others or charge for access is unresolved. What about governance? Who makes and enforces laws on Mars? If the colony is primarily staffed by American citizens employed by an American company, does US law apply? The Outer Space Treaty says that states retain jurisdiction over their nationals in space. So theoretically, an American on Mars would still be subject to US law. But enforcing that law across 55 million kilometers is impractical. You can't exactly send police to arrest someone on Mars. Moreover, what happens when the colony includes citizens of multiple nations? Whose laws apply when there's a dispute between a Chinese national and a European? Do you need some kind of international tribunal, a new legal framework specifically for Mars? These questions don't have clear answers yet. Criminal justice presents particularly thorny problems. Suppose someone on Mars commits assault or theft or, worst case, murder. On Earth, we have prisons, courts, police, forensic capabilities, and complex legal systems. On Mars, you have a small, isolated community where everyone knows everyone, no possibility of outside law enforcement, and no prison facilities. What do? You can't realistically send someone back to Earth for trial. The next launch window might be 2 years away. You can't imprison someone long-term because you don't have prison facilities and can't spare the resources. Exile isn't an option because exile on Mars means death. Do you impose fines, community service, physical punishment, the death penalty? Each option has serious problems. This isn't purely hypothetical. History shows that small, isolated communities under stress tend to develop conflicts. Antarctic research stations have had assaults. The ISS has had interpersonal tensions. Submarines have had incidents. A Mars colony would experience similar pressures, but with no realistic ability to remove problematic individuals or call in outside authorities. Some have proposed that Mars colonies would operate under something like maritime law, where the commander of a vessel has broad authority to maintain order, but giving one person dictatorial power in a closed community is ethically problematic and could lead to abuse. Alternatively, colonies might adopt some form of direct democracy where decisions are made collectively, but democracy in a small, stressed community can lead to tyranny of the majority and scapegoating. There's no easy answer here. Mars colonization would require developing new legal and governance frameworks, probably through a combination of trial and error. The first colonies would essentially be social experiments in governance under extreme conditions. Now let's talk about the ethics of planetary protection. This is the question of whether we have an obligation to preserve Mars in its natural state, or at least to avoid contaminating it with Earth life before we've thoroughly studied it. Mars might harbor indigenous microbial life, either currently active in subsurface environments or preserved in the fossil record. If we send humans to Mars without extraordinary precautions, we will inevitably contaminate the planet with Earth microbes. Humans are walking ecosystems. We carry trillions of bacteria, fungi, and viruses in and on our bodies. Our waste products contain viable microorganisms. Even our sterilization procedures can't eliminate all microbial life. If Earth microbes establish themselves on Mars, they could spread potentially outcompeting or destroying any native Martian life. They would also make it nearly impossible to determine whether any life we subsequently discover on Mars is genuinely Martian or just contamination from Earth. We'd potentially be destroying the answer to one of humanity's most profound questions. Are we alone in the universe? Before we even have a chance to answer it. Some planetary scientists argue that we should prioritize robotic exploration and scientific study of Mars for decades or even centuries before sending humans to ensure we've thoroughly investigated the question of Martian life. Others argue that human exploration is essential because humans are far more capable than robots at scientific investigation, and that the risk of contamination is worth it for the scientific and exploratory benefits humans bring. The counter-argument is that if we wait for perfect knowledge before acting, we might never act. There's always another study to conduct, another precaution to take. Moreover, Mars is a harsh environment. Any Earth microbes that make it to the surface would likely struggle to survive in the extreme cold, radiation, and desiccation. Contamination might not be as catastrophic as feared, but this is essentially a gamble with irreversible consequences. Once contamination occurs, you can't undo it. And the scientific loss would be permanent. We'd be prioritizing human presence over potentially one of the most important scientific discoveries in human history. There's also a deeper philosophical question. Do we have the right to colonize Mars at all? Some environmental ethicists argue that planets, like ecosystems on Earth, have intrinsic value independent of their usefulness to humans. From this perspective, treating Mars as a resource to be exploited or a blank slate for human civilization is ethically problematic. Mars has existed for 4.5 billion years with its own geological history and possibly its own biological history. Who are we to fundamentally alter it? The counter-argument is that Mars is a lifeless rock, or at least appears to be, and that human consciousness and civilization have value that justifies spreading beyond Earth. If Mars is truly dead, then using it for human purposes doesn't harm anything of moral significance, and if it does harbor life, that life is likely microbial, and while scientifically important, it doesn't have moral standing equivalent to human flourishing. This debate mirrors discussions about wilderness preservation on Earth. Should we leave some places untouched, or is all of nature ultimately available for human use? On Earth, we've generally decided on a compromise, preserving some wilderness while developing other areas. But Mars is an entire planet. If we colonize Mars and gradually transform it, there will be nowhere left in the solar system that hasn't been touched by human influence, except the outer planets and their moons, which present even greater challenges. Some have proposed designating certain regions of Mars as permanent wilderness areas, off-limits to development, where the planet would be preserved in its natural state for scientific study and for its own sake. This sounds reasonable, but implementing it would be challenging. Who decides which areas are preserved? How do you enforce these protections when Mars is millions of kilometers away? What happens when valuable resources are discovered in protected areas and there's economic pressure to exploit them? There's also the question of cultural heritage. If humans do establish permanent settlements on Mars, those settlements would eventually become historically and culturally significant. The first landing site, the first habitat, the first greenhouse, these would be the Martian equivalents of Plymouth Rock or the Apollo 11 landing site. Do we have an obligation to preserve these sites for future generations? And who decides what gets preserved versus what can be modified or destroyed as the colony grows? International cooperation, or lack thereof, presents additional ethical challenges. Will Mars colonization be a collaborative international effort, or will it be dominated by one or a few powerful nations or companies? The ideal scenario would be genuine international cooperation, pooling resources and expertise from around the world, and ensuring that Mars benefits all of humanity. But geopolitical reality suggests this might not happen. If one nation or company gets to Mars first and establishes a dominant presence, they'll have enormous advantages in terms of resource claims, territorial control, and political influence. This could create a new form of colonialism, not European powers colonizing other continents, but spacefaring nations or wealthy corporations colonizing other worlds while less developed countries are left behind. The Outer Space Treaty's principle that space exploration should benefit all mankind sounds noble, but there's no enforcement mechanism and no clear definition of what benefit all mankind actually means in practice. So if Mars is this difficult, what does that mean for going even farther? Can humans ever reach other star systems, or is Mars truly our limit? Click the video on your screen to find out why the answer might shock you. The physics of interstellar travel, the biological limits of human lifespan, the energy requirements of reaching other star systems. See you there.